Gemstones are supposed to come from mines, from deserts, volcanic regions, ancient mountain belts. But some of the most unexpected crystals on Earth were discovered beneath Antarctica's ice, not in mines, not in riverbeds, but inside rock that had been buried beneath glaciers for millions of years. As the ice slowly moves across the continent, it occasionally exposes fragments of the ancient crust hidden below. And inside those rocks, scientists have found something extraordinary. Gemstone minerals, crystals formed in volcanic systems, deep mountain roots, and even environments linked to Earth's mantle. Today we're exploring 10 remarkable gemstones revealed from beneath the world's deepest polar ice. Starting with the crystal that first proved Antarctica wasn't just a continent of ice, ranked 10th. Garnet, the first evidence beneath the ice. The discovery didn't begin with a gemstone. It began with a thin section of rock placed under a microscope. During early geological surveys in the trans-Antarctic mountains, researchers studying metamorphic samples noticed something familiar embedded within the crystalline structure of the rock. Deep red mineral grains, angular, well-formed, and unmistakable. Garnet. At first, the crystals themselves were not the focus of the study. The goal of those expeditions was to understand the structure of Antarctica's buried crust, the ancient continental rock hidden beneath the vast ice sheet. But garnet changes the conversation the moment it appears. Because garnet does not form randomly, it forms under very specific conditions: extreme heat, immense pressure, and slow geological transformation deep within mountain belts. When minerals inside rock are pushed beyond their stability limits during tectonic collisions, they reorganize into new structures. Garnet is one of the most recognizable results of that process, which meant the moment geologists confirmed its presence in Antarctic rocks, a much larger implication followed. Those crystals could only have formed during a period when Antarctica was part of an active mountain system. Long before the ice, hundreds of millions of years ago, Antarctica was not an isolated frozen continent. It was welded into the massive supercontinent Gondwana, connected to Africa, Australia, India, and South America. During that time, powerful tectonic collisions built enormous mountain ranges across the region. Deep within those mountains, metamorphic rocks were forming under crushing pressures, the perfect environment for garnet crystals to grow slowly inside the rock. Then the climate shifted. As Antarctica drifted toward the South Pole, ice sheets expanded across the continent. Over millions of years, those glaciers thickened until much of the original landscape disappeared beneath kilometers of compressed ice. Yet glaciers do something unexpected. They move. And as they move, they grind across the mountains buried beneath them, scraping rock surfaces and carrying fragments upward through glacial debris. That slow mechanical process is what eventually exposed the garnet-bearing rocks researchers would later study. The crystals were never mined. They were revealed, not by excavation, but by the relentless movement of ice itself. And once Garnet confirmed that deep metamorphic processes had once shaped the Antarctic crust, scientists realized something profound. If mountain-building forces had created garnet beneath the ice, then Antarctica's buried geology might be capable of producing far more complex crystals, possibly even gemstones far rarer than garnet itself. And that possibility would lead researchers to look far more closely at what the glaciers might still be hiding. Ranked 9th, rock crystal quartz. The giant crystals carried by moving ice. Some of the most striking crystals discovered in Antarctica did not appear buried deep inside rock. They appeared lying on the surface of the ice, clear, angular, sometimes large enough to catch light across the frozen landscape. Quartz. During geological expeditions across exposed regions of the trans-Antarctic mountains and surrounding glacial valleys, researchers occasionally encountered fragments of rock containing unusually large quartz crystals that had been transported by moving ice. Unlike many gemstone discoveries that require excavation or drilling, these crystals were often found in glacial debris fields, scattered across the surface as glaciers slowly pushed rock fragments outward from the mountains hidden beneath the ice sheet. At first glance, the discovery seems simple. Quartz is one of the most common minerals in Earth's crust, but the crystals themselves told a much more complex story. Quartz crystals form when silica-rich fluids circulate through cracks in rock deep underground. Over long periods of time, those fluids cool and crystallize, allowing clear hexagonal quartz crystals to grow slowly within cavities inside the surrounding stone. In many parts of the world, these crystal pockets form inside volcanic or hydrothermal environments. Antarctica, however, hides those environments beneath kilometers of ice, which raises an interesting question. If the crystals were forming deep within the rock, how did they reach the surface of a frozen continent? The answer lies in the slow power of glaciers. Glaciers are not static masses of ice. They are moving rivers of compressed snow, flowing gradually downhill under their own immense weight. As they move, they scrape against the mountains and bedrock below, fracturing rock and carrying those fragments forward across the ice sheet. Over centuries, sometimes millennia, entire pieces of the buried landscape are slowly transported outward by that movement. Quartz-bearing rocks are particularly likely to survive that journey. Quartz is extremely durable. Its hardness allows crystals to remain intact, even as surrounding rock breaks apart during glacial grinding. Eventually, pieces of those rocks emerge within glacial debris fields, where scientists conducting surface surveys can collect them for study. In other words, the crystals were not growing in the ice. They were being delivered by it. Each fragment carried by the glacier represents a small piece of the hidden geology beneath Antarctica's ice sheet, rock that formed long before the continent froze. And once researchers began finding large quartz crystals transported by glacial movement, a new realization began to take shape. The glaciers were not just revealing the continent's surface. They were slowly exporting fragments of the geological world buried beneath the ice. And if quartz crystals could survive that journey across moving glaciers, then other minerals might be traveling with them as well, possibly stones far rarer than quartz itself. Ranked 8th, Amethyst, the purple signal of Antarctica's hidden volcanoes. Among the crystals occasionally recovered from Antarctic rock samples, one color stands out immediately: purple. Not the deep red of garnet, not the clear transparency of quartz, but a distinct violet tone that geologists recognize instantly. Amethyst. Amethyst is not a separate mineral from quartz. It is quartz that formed under very specific chemical conditions that allow trace amounts of iron within the crystal lattice to interact with natural radiation over time, producing its characteristic purple color. But the real significance of amethyst is not the color itself. It is the environment required to create it. Amethyst most commonly forms inside volcanic systems. When volcanic activity fractures the surrounding rock, hot silica-rich fluids circulate through cavities and cracks within the cooling stone. Over long periods of time, those fluids crystallize along the walls of those cavities, gradually building clusters of quartz crystals. If the chemical balance is right, those crystals develop the purple coloration that defines amethyst, which makes the presence of amethyst in Antarctic geological samples particularly intriguing, because Antarctica today appears to be one of the most geologically quiet places on Earth, a continent buried beneath kilometers of ice and snow. Yet beneath that frozen surface lies evidence of a far more active past. Large portions of the Antarctic crust were shaped by volcanic and tectonic processes long before the ice sheets formed. Ancient volcanic systems once existed across parts of the continent, leaving behind mineralized rock structures capable of producing quartz and amethyst crystals. Those formations eventually became buried beneath expanding glaciers as Antarctica drifted farther south and global temperatures declined. But glaciers are powerful geological excavators. As ice sheets slowly shift across the continent, they grind against the volcanic and metamorphic rocks beneath them, fracturing the surface and transporting fragments outward through glacial debris. Occasionally, those fragments contain crystals that form deep inside those long-extinct volcanic systems. That is where amethyst begins to appear, not as massive geodes like those found in South America, but as small violet quartz crystals embedded within rock samples collected from exposed Antarctic mountain belts. Each crystal is a quiet reminder that the frozen continent was once shaped by fire as well as ice. And once geologists realized that volcanic systems had once existed beneath Antarctica's glaciers, another possibility began to emerge. If ancient volcanic environments could produce amethyst beneath the ice, then far more complex mineral systems might still be hidden within the continent's buried crust, waiting for glaciers to reveal them. Ranked 7th, Epidote, the green crystals hidden in a white continent. In a landscape defined almost entirely by white ice and gray rock, one color immediately stands out: green. Not the faint green of weathered stone, but a deep mineral tone that appears suddenly inside fractured Antarctic rock samples. When geologists encounter that color under a hand lens, they often recognize it immediately. Epidote. Unlike many well-known gemstones, epidote rarely appears in jewelry stores or museum displays. Yet in geological research, it is one of the most distinctive minerals associated with high-pressure metamorphic environments. Epidote forms when minerals inside rock begin to transform under changing temperature and pressure conditions deep within the Earth's crust. As tectonic forces reshape the crust, older minerals break down and reorganize into new structures that remain stable under those evolving conditions. Epidote is often one of the minerals that emerges during that process. Its elongated crystals and distinctive green coloration make it easy for geologists to identify even when the crystals appear only as small fragments embedded in surrounding rock. In Antarctica, epidote-bearing rocks have been documented in several exposed regions of the Transantarctic Mountains, where glaciers have carved away sections of the ice sheet and revealed portions of the continent's ancient crust. Those rocks tell a story that predates the frozen landscape by hundreds of millions of years. Long before Antarctica became covered by ice, the continent experienced powerful tectonic forces that reshaped its crust. Mountain belts rose and collapsed. Rocks were buried deep within the earth and later pushed back toward the surface as geological pressures shifted over time. During those cycles of burial and uplift, minerals inside the rocks slowly transformed. Epidote was one of the results, the crystals forming quietly within the rock, while entire mountain systems evolved around them. Eventually, those rocks were buried again, not by tectonic forces, but by ice. As Antarctica drifted toward the South Pole and global temperatures dropped, glaciers expanded across the continent, sealing much of its geological history beneath kilometers of frozen water. But glaciers never remain still. As they move across the landscape, they scrape against the bedrock below, fracturing and transporting rock fragments outward across the ice sheet. It is through that slow process that epidote-bearing rocks occasionally reach the surface, where scientists conducting geological surveys can collect them for study. In a place defined by ice and snow, those green crystals offer a rare glimpse of the continent's hidden geological complexity. Because if metamorphic systems beneath Antarctica were capable of producing minerals like epidote, then the buried crust beneath the ice may contain far more complex crystal environments still waiting to be revealed. Ranked 6th, Tourmaline, the crystal family with the most complex chemistry. Some gemstones are defined by a single chemical formula. Diamond is carbon. Quartz is silicon and oxygen. Tourmaline is different. In fact, tourmaline is not just one mineral. It is an entire family of crystals, one of the most chemically complex mineral groups known in geology. Scientists have identified dozens of tourmaline variations, each formed when different elements such as iron, magnesium, lithium, aluminum, or sodium become incorporated into the crystal structure as it grows. That complexity gives tourmaline one of the widest color ranges found in any gemstone: black, green, pink, blue, and even crystals that contain multiple colors within a single structure. But that chemical diversity also tells geologists something important. Tourmaline forms in environments where many elements are present at the same time, environments where fluids rich in dissolved minerals move slowly through cracks deep inside the Earth's crust. Those environments often occur in pegmatites, extremely coarse-grained igneous rocks that form during the final stages of magma cooling. Pegmatites are famous for producing unusual and complex minerals because the fluids inside them carry a wide range of elements that cannot easily fit into more common crystal structures. Tourmaline thrives in those conditions, which is why its presence in Antarctic geological samples is so intriguing. Fragments of tourmaline-bearing pegmatite have been documented in rock exposures within the Transantarctic Mountains, regions where glaciers have carved deep into the continental crust and exposed pieces of ancient igneous systems. These pegmatites formed long before Antarctica was covered by ice. At the time, magma slowly cooled deep beneath the surface, allowing mineral-rich fluids to circulate through the rock and create the chemical conditions necessary for tourmaline crystals to grow. Over millions of years, those rocks became part of the stable continental crust. Then the ice arrived. As Antarctica froze and glaciers expanded across the continent, those pegmatite formations disappeared beneath kilometers of ice and snow. Yet glaciers continue to move across the landscape, grinding against the rock beneath them. When that grinding fractures pegmatite veins, fragments of those mineral-rich rocks can be transported outward through glacial debris fields. That is where tourmaline occasionally appears in Antarctic geological surveys, embedded within rock fragments that glaciers have slowly carried toward the surface. Unlike quartz or garnet, tourmaline's importance lies not only in the crystal itself, but in what it reveals about the chemical environment that produced it. Because a crystal that complex could only form in a geological system where many different elements were circulating together deep inside the crust. And if Antarctica's buried crust once hosted those kinds of mineral-rich environments, then the continent's hidden geology may be far more chemically diverse than the frozen surface suggests. Ranked fifth, Aquamarine, the crystal that appears when glaciers cut into ancient pegmatites. Some gemstone discoveries begin in laboratories. Others begin in the field. Far from research stations and instruments, geological teams working in Antarctica often travel across exposed mountain belts, searching for something much simpler. Rock samples that can reveal the structure of the continent hidden beneath the ice. In those remote surveys, the most interesting discoveries often happen in places where glaciers have recently exposed fresh rock surfaces. When the ice retreats or fractures along mountain ridges, it can reveal sections of bedrock that have remained sealed beneath the ice sheet for millions of years. Those exposures sometimes reveal something unexpected. Pegmatites. Pegmatites are unusual igneous formations known among geologists for producing exceptionally large crystals. Unlike most igneous rocks that cool quickly and form small mineral grains, pegmatites cool slowly and contain mineral-rich fluids that allow crystals to grow to remarkable sizes. Many famous gemstone deposits around the world originate from pegmatite systems: Tourmaline, Topaz, and most importantly for this story, beryl. Beryl is the mineral family that includes aquamarine, the pale blue gemstone prized for its clarity and ocean-like color. When pegmatites form deep within continental crust, mineral-rich fluids circulate through fractures in the cooling rock. Those fluids carry elements such as beryllium, aluminum, and silica, the ingredients needed to grow beryl crystals. Over long periods of time, those crystals slowly develop within cavities in the rock. In Antarctica, fragments of pegmatite containing beryl have occasionally been documented in exposed rock formations along the transantarctic mountains. These discoveries are not large gem-quality crystals like those found in major mining regions. Instead, they are geological fragments, pieces of ancient pegmatite systems that glaciers have gradually exposed by eroding the rock above them. Glaciers act as enormous natural excavators. As they grind across the landscape, they strip away layers of weathered rock and transport fragments outward across the ice. That movement sometimes reveals pegmatite veins that were once buried deep within the crust. Within those veins, small beryl crystals occasionally appear. Not polished gemstones, but unmistakable evidence of the kind of geological systems capable of producing aquamarine. For geologists, the significance of those crystals is not their size or clarity. It is what they reveal about the hidden structure of Antarctica's crust. Because pegmatite systems form only in highly evolved magmatic environments, where mineral-rich fluids circulate through cooling rock. And if glaciers are exposing fragments of those systems in Antarctica, then somewhere beneath the continent's vast ice sheet, ancient pegmatite bodies may still lie buried within the rock, quietly preserving crystals that formed long before the ice arrived. Ranked fourth, Topaz, the crystal that survived millions of years beneath ice. Some crystals form under extreme conditions. Others survive them. Topaz belongs to the second category. Among the minerals occasionally identified in Antarctic geological samples, topaz stands out not because it is common, but because of how well its crystal structure can endure the immense pressures and environmental changes that occur deep within continental crust. Topaz forms in environments rich in fluorine, typically within granitic systems where magma cools slowly and mineral-rich fluids circulate through fractures in the surrounding rock. Under these conditions, aluminum, silicon, oxygen, and fluorine combine to form one of the most structurally stable crystal lattices found in the gemstone world. That stability is part of what makes topaz so remarkable. Unlike many minerals that deform or break down under changing geological conditions, topaz crystals can remain intact for extraordinary lengths of time, even as the surrounding rock undergoes tectonic pressure, uplift, and erosion. In Antarctica, fragments of fluorine-rich granitic rocks have been documented within exposed sections of the Transantarctic Mountains. These formations are part of ancient crustal systems that developed long before the continent was covered by ice. When those granitic systems cooled deep underground, they created the chemical conditions necessary for minerals like topaz to crystallize within fractures and cavities inside the rock. For millions of years, those crystals remained locked inside the continental crust. Then Antarctica froze. As global temperatures declined and ice sheets expanded across the continent, glaciers gradually buried much of the landscape beneath kilometers of compressed ice. Entire mountain systems became sealed beneath the expanding ice sheet, but glaciers also reshaped the land beneath them. As ice slowly flows across the continent, it grinds against exposed rock surfaces, fracturing the bedrock and transporting fragments outward across glacial debris fields. Occasionally, those fragments include pieces of ancient granitic systems that contain topaz crystals preserved within the stone. These crystals are rarely large. Often, they appear only as small, transparent grains embedded in the surrounding rock. Yet their survival tells an important geological story, because the journey from deep crustal formation to exposure on the surface is not gentle. Over millions of years, those rocks have endured tectonic pressure, uplift, glacial grinding, and extreme temperature changes, conditions that destroy many other minerals. Topaz survives them, and that durability allows it to act as a kind of geological time capsule, preserving evidence of the chemical environments that once existed deep within Antarctica's crust. But even crystals as stable as topaz only tell part of the story, because some minerals found in Antarctic rocks record events far older than the mountain systems themselves. Crystals capable of preserving information from the earliest chapters of Earth's history. And those crystals begin to appear in the next stage of the story. Rank third. Zircon, the crystal that carries Earth's deepest history. Some gemstones are valued for their color, others for their rarity. Zircon is valued for something far more extraordinary: time. Among the minerals occasionally recovered from Antarctic geological formations, zircon holds a unique place in Earth science because of its remarkable ability to preserve information from the earliest chapters of the planet's history. Zircon crystals form when zirconium-rich minerals crystallize within cooling magma deep inside the Earth's crust. As those crystals grow, their internal structure becomes extremely stable, so stable that it can survive geological events that would destroy most other minerals: heat, pressure, tectonic collisions, even the slow transformation of surrounding rock during metamorphism. While other minerals dissolve, deform, or recrystallize, zircon often remains intact. That durability allows zircon to act as a kind of geological archive. Inside the crystal lattice, tiny amounts of radioactive uranium become trapped during formation. Over immense spans of time, that uranium slowly decays into lead at a predictable rate. By measuring that process, geologists can determine the age of the crystal with extraordinary precision. Some zircon crystals on Earth have been dated to more than 4 billion years old. That is older than most of the planet's existing crust. In Antarctica, zircon-bearing rocks have been identified in several regions where glaciers have exposed fragments of the continent's ancient geological foundation. Those rocks are part of the East Antarctic Craton, one of the oldest surviving pieces of continental crust on the planet. Long before Antarctica became an isolated polar continent, This crust formed during the earliest stages of Earth's tectonic evolution. Within that ancient rock, zircon crystals quietly recorded the passage of geological time. Then the ice arrived. As Antarctica drifted southward and ice sheets expanded across the continent, those rocks were buried beneath kilometers of frozen water. Yet glaciers continue to reshape the landscape beneath them. As they grind across the bedrock, they fracture ancient rock formations and transport fragments outward across exposed mountain ranges and glacial debris fields. Within some of those fragments, zircon crystals remain embedded exactly where they formed hundreds of millions, sometimes billions of years ago. When scientists recover those crystals today, they are not simply studying a gemstone. They are studying one of the oldest surviving records of Earth's early geological history, a crystal that began forming long before Antarctica froze, long before the continents took their modern shapes, and long before the ice sheet buried the landscape where it formed. Yet even zircon, a mineral capable of preserving billions of years of planetary history, does not represent the most extreme conditions hidden beneath Antarctica's crust. Because deeper within that crust, far below the reach of glaciers, pressures exist that can create something even rarer. Crystals form not just in ancient rock, but deep within the mantle itself. Ranked second, blue sapphire, the crystal forged under crushing pressure. Some gemstones form slowly. Others form under forces so immense that the surrounding rock itself begins to transform. Blue sapphire belongs to the second category. Sapphire is a variety of the mineral corundum, composed primarily of aluminum oxide. In its pure form, corundum is colorless. But when trace elements such as iron and titanium become incorporated into the crystal structure during formation, the result can be the deep blue gemstone known as sapphire. What makes sapphire geologically remarkable is the environment required to create it. Corundum forms only under conditions where aluminum-rich rocks experience intense pressure and temperature, but remain relatively low in silica. In most geological environments, silica combines with aluminum to form other minerals before corundum crystals can develop. But when the chemical balance is just right, and the pressure is extreme, corundum begins to grow. These conditions are most commonly found in high-grade metamorphic environments deep within continental crust, where ancient rocks are compressed, heated, and transformed during tectonic collisions. That type of environment once existed beneath Antarctica. Long before the continent froze, powerful tectonic forces shaped large portions of its crust as part of the ancient supercontinent Gondwana. During those events, mountain systems rose and collapsed, and deep metamorphic zones developed within the continental interior. Within those zones, the pressures were high enough to allow corundum crystals to form. Fragments of these high-grade metamorphic rocks have been identified in exposed Antarctic mountain belts, particularly along the Transantarctic Mountains, where glaciers have carved through sections of the buried crust. Within those rocks, corundum occasionally appears, not as polished gemstones, but as small crystalline grains embedded within metamorphic stone. Geological evidence of the extreme conditions that once existed deep beneath the Antarctic landscape. Their presence reveals something important about the continent's geological past. Because sapphire cannot form in ordinary crustal environments, its existence requires immense pressure, unusual chemistry, and long periods of geological transformation. In other words, the kind of forces capable of reshaping entire continents. Yet even the crushing pressures that create sapphire occur within Earth's crust, still far above the deepest geological environments hidden beneath Antarctica. Far below the metamorphic zones where corundum can form lies another region entirely, a realm where pressures are far greater, where temperatures climb even higher, and where the most famous gemstone on Earth is born, a crystal created not within the crust, but deep within the mantle itself. In first place, diamond, the crystal that may be hidden beneath Antarctica's ice. For centuries, diamonds have been associated with deserts, mines, and ancient riverbeds. Africa, Russia, Canada, places where deep geological processes have pushed fragments of Earth's mantle close enough to the surface for humans to reach them. Antarctica seems like the last place anyone would expect to find a diamond, a continent buried beneath kilometers of ice, a landscape so remote that almost nothing has ever been mined there. And yet the geology beneath Antarctica tells a very different story. Diamonds do not form inside Earth's crust where most gemstones develop. They form far deeper, roughly 150 to 200 kilometers beneath the surface, inside the upper mantle, where pressures become so immense that carbon atoms are forced into one of the most tightly bonded crystal structures known in nature. Once those crystals form, they remain trapped deep underground unless a very specific type of volcanic eruption occurs. These eruptions produce kimberlite, a rare volcanic rock capable of transporting mantle material rapidly toward the surface. Around the world, nearly every major diamond deposit is associated with ancient kimberlite systems. And in recent decades, geologists studying Antarctica have identified something remarkable. Minerals typically associated with kimberlite systems, including certain mantle-derived indicator minerals, have been found in rock formations within parts of the Antarctic crust. These minerals do not prove that diamonds have been recovered from Antarctica, but they reveal something much more intriguing. The deep geological conditions required to produce diamonds may exist beneath the Antarctic continent. Long before the ice sheet formed, Antarctica was part of the same ancient continental systems that host diamond deposits in Africa and Australia today. The crust beneath East Antarctica contains some of the oldest and most stable cratonic regions on Earth. The same kind of deep continental roots where diamond-forming mantle environments often develop. If kimberlite eruptions occurred in those regions millions of years ago, the volcanic pipes they created may still exist deep beneath the ice, sealed beneath kilometers of frozen water, untouched, unexplored. Antarctica's ice sheet hides more than mountains, valleys, and ancient rock. It hides an entire continent of buried geology, a landscape that may contain mineral systems as complex as any found on Earth. And if diamonds do exist beneath that ice, they may remain there longer than any human civilization has existed, waiting in darkness, far below the glaciers, where the deepest processes of our planet quietly continue shaping crystals beyond the reach of the surface world. Antarctica may look like a silent continent of ice, but beneath that frozen surface lies one of the oldest geological landscapes on Earth. Ancient mountains, buried volcanic systems, fragments of crust that formed billions of years ago. As glaciers continue to move across that hidden continent, they slowly expose pieces of the rock beneath them, and occasionally the crystals formed inside it, some familiar, some unexpected, and some that may still be waiting beneath kilometers of ice. Because Antarctica's greatest geological discoveries may not have happened yet, they may still be hidden beneath the ice,